Hi folks, so in this little segment of Lecture D2, I just want to go over the kind of exponential family of random variable distributions, which include 3 continuous and 1 discrete. And so I'm going over this so that it's clear what sort of the differences are, because I don't want anyone to mistake a Poisson random variable for an exponential random variable, but I also want you to know the relationship between the two, because there is kind of a very important relationship. So here's your exponential random variable. It's PDF, its probability density function is shown over here. It's got a mode right at 0, and then it falls off after here, and then its cumulative distribution goes then the other way. So rather than having an S shape like many cumulative distribution functions, it has this diminishing marginal returns where it's constantly rising but then slowing down as it goes. So this distribution is very often used for thinking about service times, failure times, etc. Time is the big thing here because it has infinite support, but it's infinite non-negative support, which means it can be any number from 0 to infinity, but it can't be negative. And so it's an easy one to do for time because you very often don't know how long something's going to last, and so an exponential is kind of a good guess at that. All right, so the interesting features of an exponential: the mean of an exponential happens to be equal to its standard deviation, so it is a single parameter distribution. If you know lambda, you know everything. You know its mean, its variance, its standard deviation. So that is singly defines its shape. It's memoryless, which basically means that so what this statement here means is the probability that x is greater than x plus y, given that we already know we're in a world where x is greater than x, is just the same as the probability that the, again, random variable x is greater than y alone. So in other words, if I know that I've already waited 10 minutes, what's the probability that I'm going to wait at least another 5? Well, if I know for sure that I've already waited 10, that's just the probability that I'm going to wait 5 from the same exponential distribution. So you don't get anything by knowing you've already waited 10. That's kind of lost time, so it's memoryless, and so that's kind of what I'm saying down here. All right, so that's fine. Let's say you have an exponential that is modeling the failure times of redundant components. And so you've got a light bulb that is in use. You wait for it to fail. When it fails, you put a new light bulb in. You put a new light bulb in. When that one fails, you put a new light bulb in. When that one fails, and so on. Well, so the question is, if you bought a box of 6 light bulbs, then how long until the whole box has failed? And so that is effectively what the so-called Erlang K distribution is. The K is how many exponentials you're summing up. So it's just that. So an Erlang 1 distribution is just an exponential distribution. If you look at the probability density function here, if you set K equal to 1, this guy goes away right here, and this just becomes a lambda. And this also goes away. And if you look at it, lambda e minus lambda x, that is exactly the PDF of an exponential. So an Erlang 1 is an exponential. That's like kind of like a good little piece of trivia for like a midterm or something like that. But those two are identical. So an Erlang is a generalization of an exponential with this new shape parameter k, which is interpreted as the number of exponentials you're adding together, but you're still describing the time if you were to wait, if you're waiting that many exponentials. So the mean is k over lambda, and the variance is k over lambda squared. So again, very similar to a normal exponential. So it's very, very exponential-like. And so it's used in queuing systems, and there's tons of times that if you've modeled a service time or an inter-arrival time or whatever, like just think about inter-arrival times. If you just simply want to know, if you know that your inter-arrival times are described by an exponential, and you want to know how long until my 10th customer gets here, well, that's an Erlang 10 distribution. Okay. Very different distribution is a Weibull distribution. So an Erlang distribution added this shape parameter k, and it changed the kind of shape from an exponential to all these other funny shapes here, and we interpret that shape parameter, in this case, as the number of exponentials you're adding together. A Weibull doesn't describe a sum of exponentials. It kind of describes a way in which you can think of the exponential rate sort of changing over time. So an exponential can be thought of as a failure rate with kind of a constant rate of failure. And so if you say that something has an exponential distribution with a rate of 2 failures per year, then that doesn't mean you're always going to get 2 failures that year, but it means the mean time between failures is going to be half a year. And so that's going to be kind of like a that's going to be sort of this consistent kind of constant rate. Now you could imagine that you could have things where it's more likely that you're going to fail early than late, and or it's more likely that you're going to fail late than early. And so if we look at the distributions of the density functions here, so this is your exponential, where it kind of falls off, so it's sort of very unlikely that you're going to fail out here. So if the mean is like right here, this kind of tells you how likely it is you're going to fail far more than the mean or far less than the mean. All right, so these other ones, like this weird ski slope here, you see that has this extra shape parameter k equals 0.5 that is going to put a bunch of the density right here at near 0. So that means that you can see the cumulative distribution rises super quickly and then falls off. That means that many of the events happen very early, much earlier than you would expect if it was an exponential distribution. Likewise, if we take that k parameter and make it longer, then that kind of guarantees that almost no failures are going to happen here, which is why the cumulative distribution is flat and then suddenly rises. And so the probability that you'll get a failure before this time is basically 0. That's what this cumulative distribution is all about. And so this is saying that the kind of the mode of the density is right on here, so you get kind of sort of a central location where most of your failures happen, and then they fall off very quickly too. So a Weibull distribution has the ability to think about these reliability things where you have things that you fail kind of more often than exponential, more often than random, and less often, or more early than random and more late than random. But it also will typically be used, and not necessarily in a good way, just to fit other distributions. Like if you look at these densities, like you've got things that look exponential, you look like things that look like a so-called Pareto distribution, you get things that kind of look like a Gaussian. So with the single shape parameter, you can get all sorts of other different types of distributions. And so when we start fitting distributions to data, and you use some of the automatic tools that the computer will provide, it will very often spit out a Weibull as a best fit, just because it has so much sort of it has so much flexibility. And but in the end, I only want you to use a Weibull distribution if you really can't resort to anything else, or you have good intuition that the Weibull gives you some interesting perspective on the system in terms of like failure rates or something like that. Okay. So now we move on to a Poisson. Now a Poisson random variable is discrete. It has a probability mass function. So that's what we see up here. And that's why there's all these little dots. So disregard the interpolating connecting lines here in this probability mass function, PMF, in this cumulative distribution function. So a Poisson distribution, it only is supported by these non-negative integers, 0, 1, 2, up to infinity. And you can think of it as the number of events occurring in a fixed interval of time if the inter-arrival time between those events are independent and if the arrivals have an average rate. Now, what that means, so implicitly what's that saying here? If you have independent inter-arrivals that have a given average rate, that actually necessarily means that they are exponentially distributed. So with this rate, lambda. So what this is saying is that if effectively what a Poisson random variable is if you have an exponential generating you inter-arrivals with a rate lambda, and you ask how many arrivals do I get that are spaced by that exponential in a particular interval t, then that's what gives you the parameter for this Poisson, and this Poisson will tell you the distribution of the number of arrivals you'd expect in that interval. So this alpha parameter is just effectively the average number of arrivals in a particular interval. So if your interval is 1 year and your lambda is 2 per year, if you multiply 2 per year times 1 year, then you say you get an average number of 2. So of course, that's what we just said, 2 per year. So if I did 2 per year times a year, I get 2 out of here. So then I go into my probability mass function, I put a 2 in for the alpha here, and then I ask for k sweeping from 0 to infinity, what does that distribution look like? And that tells me that that even though on average I get 2 per year, sometimes I'll get 5, and sometimes I'll get none, and so on. So that's what a Poisson is. It is the count of arrivals that are spaced by exponential inter-arrivals in a particular interval, where the parameter is the rate of that exponential times whatever the length of the interval is. Okay, so that's basically the end of the exponential family. I do want to mention one more that's at least related. So there is this thing called a negative binomial, and in a negative binomial, this is basically the number of trials you need to get. If you flip a coin, how many coin flips do you need until you get a certain number of heads? They aren't necessarily in a row, but just, if I flipped the coin 100 times and I got 5 heads, well, how many times do I need to flip it to get 10 heads? Now, if you say, well, I actually want r is equal to 1, so if I actually want to say how many times until I get a single head in my coin flips, then that is actually the kind of discrete time version of an exponential. So the number of trials in a Bernoulli random variable in sort of a coin flip, the number of coin flips until you get a success is described by effectively a length of time in terms of time steps that is exponential. So this is the discrete analog of the exponential distribution, is the geometric distribution. So if you were to look up at this here, imagine if r was equal to 1. Well, then this would be p to the 1, so just be p. And this would be 1 minus p, k minus 1. Okay, so so if you think about k minus 1, I could just make that to the k divided by 1 minus p. So I would end up effectively getting a bunch of constants here. So p is a constant, and then that constant would be raised to the k. Well, that's an exponential. I mean, an exponential is a constant being raised to the argument of, in the exponential's case, the probability density function. In this case, the probability mass function. So this is the discrete analog of an exponential right here. So that's kind of just a little fun tidbit, but when I talk about the exponential family, I'm mainly referring to the exponential, the Erlang, the Weibull, and the Poisson. So know the differences between those and how you might use them differently, and how you might get tripped up between like the difference between a Poisson random variable, which is different than a Poisson process, and exponential. Okay.